This talk is brought to you by the Bamberg Mathematical Consciousness Science Initiative.
Thank you, Johannes, and thank you, Andrew, for having me. I'm so humbled to be able to speak at BAME. I guess that's how you pronounce it, or BAME if you're American, maybe. Given the amazing lineup that we've been able to learn from these days, me being a you know an amateur in philosophy, coming from biology mainly and math. Um, it's just a real pleasure to learn from the eloquence with which all of you have been dissecting these relevant elements and frameworks to this sort of overlapping zone of research interests. So the title of my talk could have been a bit more aligned with that moment of being humble. It could have been a bit more modest, like towards a geometric neurophenomenology. And then I might have specified also of a joint action or any other sort of like specifically paradigmatic uh, phrase after that. Um, what I mean by that is that this is the attempt of building, of course, towards a framework um, that I'm titling that. But here we are, so let's just go with it. And you'll see what has been accomplished so far and what is future work or the outlook. So the attempt is to connect three things. First, the lived experience of acting together with others. Second, the neural dynamics of interacting brains measured with hyperscanning. And third, geometric descriptors of those dynamics that can be used inside generative models. So the background is a slightly older story. Back in 2013, during my undergrad studies, I heard Carl Friston speak at the Berlin School of Mind and Brain about active inference as a candidate unifying language for brain and behavior. And yesterday, I gave a talk for his theoretical neurobiology group at UCL, which in a sense is my way of returning to that moment and asking, can we develop such a language that is rich enough to describe neurophenomenological aspects of a given target domain of interest? So whether this comes from milliseconds or minutes and from local circuits up to social coordination is then the question at hand, the sort of multiscalar slice that we choose to um, take upon ourselves to research on. And active inference gives us the generative story um, for uh, for this attempt. And what I'm adding, in a sense, is just a geometric observable specific to interbrain connectivity that is both robust enough for naturalistic settings or experimental paradigms, yet also subtle enough to pick up phase transition like changes across the scales that we choose to operate within. So the overarching question is how this can inform a prospective geometric neurophenomenology of joint action and how that connects to questions of collective or shared intelligence. Let me see if I can. Yeah, I think that worked, right? Cool. So, as I was saying, this talk builds on three interrelated topics. And for now, it also builds on three interrelated papers, but which are leaning more heavily towards the second aspect or topic that I named. Um, First of the two that are screenshotted there are on their way to become part of the proceedings of some workshops. And the third one will be sent out for a review by the end of the year, which comprises the actual toolkit that I built with my colleagues to measure via geometry interbrain networks as collected via hyperscanning. It also draws the general talk inspiration from the interactive turn, which argues that being on the same wavelength is a neurobiological reality across neural, behavioral, physiological, and other channels. So that's perhaps the first sort of ontologic or epistemic sort of claim that is smuggled in to what's to come. And let me briefly outline what is to come. First, I'll motivate joint action as a target for consciousness science and sketch what I mean by neurophenomenology in perhaps a mathematical sense. Second, I'll take a measurement theoretic look at common inter-brain synchrony metrics, um, things like PLV, coherence, Granger, transfer entropy, inter-subject correlation. That will help us to introduce a more generative and geometric view afterwards. Third, I'll introduce generative models of interacting agents in the spirit of active inference, including a simple formal model of affect as recursive inference over self-model coherence. Fourth, I'll describe geometric hyperscanning. We build time-resolved inter-brain networks from dual brain recordings, compute discrete Ricci curvature across them, and track the curvature entropy as an order parameter for coordination regimes and phase transitions. Fifth, I'll talk about how we try to connect those geometric signals to first-person structure via microphenomenological reports and annotations. And finally, I'll sketch how this extends from dyads to collectives, including possibly human-human, human-AI, and AI-AI constellations, and how curvature thresholds might serve as signatures of joint or collective agency. Here we go. So I make the claim that much of consciousness science and social neuroscience overlap or have in common that they focus on single brains observing stimuli or other people. We take a second person neuroscience perspective. Social neuroscience, according to second person neuroscience, is studied and must be studied during real-time reciprocal engagement. And by joint action, I mean here situations where agents coordinate their behavior in time towards shared or at least mutually constrained goals, such as playing music together, co-narrating a story, or solving a problem jointly. Phenomenologically, such situations come with a distinctive sense of we-ness. It's a further claim to this. So, feeling as if one is acting with someone, not just alongside them. From this viewpoint, the dyad is a natural unit of analysis. The relevant processes are not only inside each brain on their own, but they live in the interaction itself. And so that interaction becomes the medium of meaning. We also know that being on the same wavelength is not just a metaphor. With hyperscanning, we can measure coupling across neural, physiological, behavioral, and other channels, as we were saying. And the challenge is to develop a formal language that captures how these multimodal coordination patterns relate to the structure of experience. So I'm using the term neurophenomenology very deliberately in Varela's original sense. From what I have understood so far, it combined, first-person reports with neural dynamics, treating both as first-class data and looking for structural correspondences. Here, I take a more explicitly computational and perhaps specifically geometric turn. On the phenomenological side, we use microphenomenological interviews. I've been also thinking of dual ethnography protocols and fine-grained timeline annotations by experts on the specific paradigms that are employed in the lab settings, so as to reconstruct the structure of experience during joint tasks, shifts in attention, felt togetherness, moments of breakdown and repair, you name it. On the neural side, we summarize dual brain dynamics, not just with raw synchrony, which is sort of the point of departure historically for me with this research agenda, trying to improve synchrony as such via geometric observables, particular the discrete Ricci curvature and the entropy of its distribution over set interbrain networks. The goal is to align latent interaction states in a generative model simultaneously with these geometric signals and with phenomenological structure, so that experience, dynamics, and the model all talk to each other. So before we go into geometry, let's pause a bit on the measurement theoretic point that I had mentioned. Hyperscanning studies often report IBS interbrain synchrony using metrics like phase locking value, coherence, Granger causality, transfer entropy, etc. These metrics have proven useful across a broad array of studies in social neuroscience, but they're often treated as if they directly measured social interaction itself, which is a bit misleading. They are very sensitive to shared stimulus confounds. So if two people watch the same movie, you can get high synchrony without any interaction whatsoever. They are vulnerable to field spread and leakage, especially in EEG and MEG. And they often assume some degree of stationarity and linearity, which is not really warranted in real interaction. So if we take measurement theory seriously, we do have to ask, as what we were foreshadowing before we began, namely, what is this metric actually estimating? Under what assumptions? This is one motivation for moving towards a framework where the observable is explicitly related to latent interaction states in a generative model, and where we use tools, including geometry, that are perhaps less assumption laden than simple linear synchrony. So our theoretical backbone is active inference, where each agent maintains an internal generative model of how it expects the world to be, including a model of itself. The agent perceives sensory input, compares predicted with observed data, and minimizes variational free energy by updating beliefs or by acting to make observations fit those expectations. In a social context, our generative model includes a model of you and your likely actions, and your model includes me. So we have two coupled generative systems interacting. Each person is not just predicting the environment, but they're also predicting the other's actions and reactions. This gives rise to continuous feedback loops. I predict what you'll do, act based on that, you observe and update your model, you act, I update, and so on. Rather than thinking of this as an infinite regress of I model you, model me, modeling you, we can treat the dyad itself as a single coupled system with its own dynamics, which is what we're trying to formalize. When two agents engage, their generative models become coupled, as we were saying, effectively forming what we can call a shared generative manifold. This is a fancy way of saying that the two people plus their interaction can be considered one integrated system, at least for modeling purposes. In this regime, the self-other boundary becomes somewhat fluid. Each person's brain and body states are tightly entangled with the other's actions and predictions. So my next action depends on my internal state and on what I expect you to do, which in turn depends on what you expect me to do. As we were saying, instead of an infinite hierarchy of I think that you think that I think, we treat the dyad as a single system with internal states and policies defined on a shared manifold. Phenomenologically, this is where the sense of we can arise, feeling that the locus of control and experience is partially shared. Our question is, can we say something precise about the geometry of this shared manifold? And can we relate that to the structure of lived joint experience? Joint action is not affect neutral. It is imbued with emotion, frustration when coordination fails, relief when repair succeeds, or sheer enjoyment when things flow. And that's why we model valence as an ongoing inference about the integrity of the self model, as an appraisal of how well my identity relevant expectations are being met. In our formulation, valence is driven by two main factors. First, the magnitude of self-related prediction error, so how surprised I am about myself in the situation. And second, the self-relevance of that error, how much it matters to my identity or core goals. We also include an effective memory component, capturing the, let's say, inertia of that mood, and also a temporal aiming component, which describes how far backward and forward in time my appraisal extends. The key idea here is that affect is not just a reactive label, it is a recursive inference about self-coherence under uncertainty. And in interaction, these affective inferences are tightly coupled across agents. So let's actually put this together at the dyadic level. In interaction, each person's sense of self-coherence is co-constructed with the other's behavior, going back to second person neural. You're constantly receiving social evidence that can either stabilize or destabilize your self-model, and you're doing the same for your partner. And this leads to what has been characterized as rupture, repair, and re-attunement cycles. A rupture occurs when something triggers a sudden misattunement, such as a misunderstanding, a mistimed response, you name it. In our model, this corresponds to a spike in one or both partners' self-related prediction errors. In a repair phase, the partner attempts to restore that coherence, and they adjust beliefs and actions. So they might clarify, rephrase, change tone, re-engage. In modeling terms, they explore new policies to reduce the prediction errors that cause the rupture. And if that repair process is successful, they reach reattunement, a new stable regime of coordination. The dyad may return to a previous pattern or settle into a qualitatively different one, but in either case, there is a regained sense of we-ness and corresponding balance. Our hypothesis is that these phases correspond to distinct regions of interest at the brain level and transitions in the geometry of the interbrain network formed by both brains, which we can try to detect. So, little excursion into hyperscanning. Hyperscanning gives us simultaneous recordings from multiple brains during interaction. And traditionally, analysis, as we had said before, have relied on relatively simple synchrony metrics. This is not to bash on them by any means. Simple is a technical euphemism, just to say that while they're useful, they're limited insofar as they are descriptive averages. They might tell you that on average, the two brains were moderately synchronized during the task, but they do not tell you when or how the pattern of coupling changed moment to moment. They often assume linearity and stationarity, as we had said before, but real interactions involve non-linear changes and non-stationary dynamics. So abrupt shifts in coordination are exactly what we should care about. Hence, we should be able to model them. They also tend to conflate synchrony from shared input with synchrony from genuine interaction. So two people watching the same flashing stimulus may have correlated oscillations even if they ignore each other. To move beyond this, we need tools that look at the structure of interbrain coupling, both its topology and geometry, rather than just its average magnitude. Discrete network geometry gives us that. It lets us ask how the shape of the interbrain network evolves over time and whether there are phase transition-like changes in that shape that align with interactive events. Concretely, here's how we construct an interbrain network from hyperscanning data. We start with dual EEG, fNIRS, or fMRI recordings from two participants engaged in a joint task. I'd mentioned MEG before, but it's just less done or less performed. We then define nodes as either recording channels or regions of interest, depending on the modality that we're using, for both brains. So some nodes belong to person A, some belong to person B. For each time window, say a few milliseconds up to a couple of seconds, we compute a functional connectivity measure between each pair of nodes, within each brain and across brains. This could be coherence, phase locking, or a more robust synchrony metric, ideally after controlling for leakage and shared input. These connectivity values become edge weights in a graph. We have within brain edges and cross brain edges coexisting in a single network. By sliding the analysis window across time, we obtain a sequence of graphs with those weights, each representing the current pattern of within and between brain coupling. The question is, how can we characterize the shape of these graphs as they evolve in a way that is sensitive to structural reorganization and not just average synchrony? One powerful set of tools comes from discrete network geometry, which is where we're borrowing mainly from. We use the Forman-Ricci curvature, which is an edged base quantity that tells us whether an edge is embedded in a redundant cluster or acts as a unique bridge. So intuitively, consider an edge linking nodes I and J. If I and J share many neighbors and there are multiple alternate paths between them, the edge has a high positive curvature. It sits in a dense redundant neighborhood. And if you remove it, the network remains well connected. If instead the edge is the only link between two communities, there are just few or no alternative paths, then its curvature is low or negative. And removing it fragments the network. It becomes a bottleneck or a bridge. Applied to interbrain network, positive curvature edges lie in tightly coordinated clusters of regions, positively reflecting modules that are jointly recruited in coordinated states, whereas negative curvature edges mark critical bridges between those modules. For instance, key cross-brain links that hold the joint network together. So curvature gives us a local measure of structural role. Is this connection part of redundant support, or is it carrying something uniquely important? At each time point, we don't just have a single curvature value. We have a distribution of curvature values over all edges in the interbrain network. We summarize this distribution with curvature entropy, defined as the Shannon entropy of the curvature values after a suitable normalization. We'll look into different kinds of entropies in the future, but we've stuck with this for now. If most edges have similar curvature, say all moderately positive, then the entropy is low. The network topology is then relatively homogeneous. Structurally, the graph then looks similar everywhere, which may suggest a stable configuration. If instead some edges have a very high curvature and others have very low or negative curvature, then the distribution is broad and the entropy is high. The topology is then expected to be heterogeneous. There are tightly clustered subgraphs coexisting with sparse, fragile bridges. This might indicate that the network is in a reconfiguring or transitional state. So by tracking this entropy over time, we get a single scalar that acts as an order parameter for interbrain topology. And abrupt changes in it, say spikes or drops, can flag phase transition-like events in the coupling between the brains. So this is the quantity that we'll use as a neural marker of rupture, repair, and re-attunement. But before looking at real data, we tested curvature entropy on toy networks, where we know what the phase transition looks like. We start with the regular lattice, an ordered network where each node is connected to its neighbors. And then we gradually introduce randomness by rewiring edges with increasing probability in the spirit of the Watt-Strogatz small world model. Also used Kuramoto's, which by our co-author, Professor Dumas, has been shown to be very robust for this same purpose. And jumping over perhaps the details here, it's exactly what you'd expect from an order parameter in physics. If instead we look at a simple synchrony or correlation measure of the function of this, we typically see a smooth change with no sharp signal at the critical point. In other words, traditional synchrony metrics miss the phase transition that curvature entropy picks up. So this gives us some confidence that if we see sharp changes in curvature entropy in real interbrain data, we should interpret those as potential structural transitions in coordination, not just model noise. So this brings us to maybe a more conceptual point, namely, why bother with geometry at all? And as I was trying to point out before, traditional or canonic, let's say, synchrony metrics reduce complex patterns of interaction to a single value. They can remain moderate or high even while the pattern of connectivity changes drastically. So they tell you how much coupling there is in an aggregate, but not how that coupling is organized. So network geometry via curvature tells us whether connections are organized in dense, redundant clusters or bridge-like structures. Curvature entropy then tells us whether that organization is stable or diversified and reconfiguring. So in a way, geometry gives us an early warning of structural reorganization. A spike in curvature entropy can flag the onset of a rupture before average synchrony has fully dropped. At the same time, none of these metrics, of course, we need to remember are causation. To talk about influence and flow, we have to complement geometry with information theoretic measures. So mutual information, transfer entropy, partial information decomposition, to ask who is driving whom ideally, and whether multiple channels are redundant or synergistic. The picture that I'm trying to advocate for here is one of integration. You use geometry to track the shape and phase transitions of interbrain networks, and use information theory to characterize dependence, directionality, and synergy. So together, we hope they'll yield a much richer and more robust description. Oh, there we go. So now we can hopefully close the loop between the conceptual rupture repair cycle and the geometric observables. Our working hypothesis is that during a rupture, when misattunement and surprise are high, the interbrain network undergoes a structural reconfiguration. Edges change their roles. Some clusters break, new bottlenecks appear. So we expect curvature entropy to spike, reflecting this heterogeneity. Average synchrony often drops. So subjectively, valence might be negative in this classical setting. Whereas during repair, the dyad explores new ways of relating. From the perspective of the network, the system is searching and different configurations are tried out. Curvature entropy may fluctuate as the network tests patterns and rejects some. And synchrony may begin to recover, but can be unstable. So here the subjective experience would be expected to be mixed, effortful, hopeful, probably frustrating. With successful reattunement, at last, a new pattern of coordination stabilizes. The interbrain network settles into a more homogeneous topology, curvature entropy drops to a lower stable baseline, and synchrony recovers. Valence should become positive again, and the participants would report this renewed sense of we-ness. So we hope that these phase transitions can also be regressed against and or observed at multiple levels, as we were foreshadowing, both in neural measures, in behavior, through gaze, prosody, posture, turn-taking, and also experience. The task then of geometric neurophenomenology will be to align those levels and to see whether we can give operational definitions of rupture, repair, and reattunement in terms of geometry and geometric and information theoretic markers. So far I've focused on dyads, but the same idea should extend to multi-agent systems. We can build a multi-brain network where nodes come from all participants, and we can compute curvature and curvature entropy on this larger graph and consider the group as a single multi-agent generative system. There's a computing threshold, of course, that we'll need to optimize for, and we're already seeing the difficulty in this with an interactive F-nurse data set where both participants are wearing VR headsets. You must imagine the weighted connectivity matrix needing to be coupled to two further spaces of 3D vectors, right? The ones in real space and the ones in virtual space. So this becomes increasingly complex for sure as we move towards more naturalistic settings. But still, we should be able then to ask, are there phase transitions where the group switches from behaving as a loose collection of individuals to something more like a unified team or collective with emergent shared intelligence? That's just a conjecture for now. But as coordination improves, the network's geometry might reorganize into highly integrated modules spanning multiple agents. And curvature entropy might first rise as the system explores configurations, then drop as stable team organization emerges, and so forth. This might correspond phenomenologically to the we mode in group flow. We hope that this is not limited to humans. So we want to test and monitor similar network level quantities in human AI or AI collectives. More of that to come in the next year. The broader idea, which I sometimes call or wish to call a generative geometry of collective intelligence, that's what I called it yesterday, is to combine active inference with geometric and information theoretic observables to quantify emergent coordination across scales, so from dyads up to large collectives, biological or artificial. So I would briefly try to connect this back to mathematical consciousness science. I've tried to sketch a formal linkage between first generative models of interacting agents, inspired by active inference and predictive processing. Second, geometric descriptors of interbrain dynamics, especially discrete curvature and curvature entropy, treated as order parameters for coordination regimes. Third, the phenomenological structure of joint experience accessed via microphenomenology and aligned with latent interaction states. And I'd hope that this raises a number of mathematical questions. And we identify invariants of joint action manifolds, whether those are geometric or information geometric quantities. Only the future can tell. And we have rigorous, maybe axiomatic definitions of rupture, repair, or even we-ness in terms of properties of these manifolds. And how do these structures scale with group size, with heterogeneity of agents, with different sensory and cognitive architectures, especially in the context of artificial systems or the possibility of them. So these are the kinds of questions where I seek to collaborate with mathematicians, neuroscientists, philosophers, as they seem both necessary and promising to me. I hope this gives a sense of how a geometric neurophenomenology might contribute to those questions, to solving them. And yeah, thank you for your attention. And I look forward to the questions and the discussion.